How's it going, everyone? My name is Griffin Furlong. I am a professional civil engineer, and in today's video we are going to walk through stage storage and curve number calculations of a wet detention pond. If you haven't watched the last video, I highly suggest you do so. I will say that this video is meant for beginners, so if you are an expert civil engineer, I don't think this one's for you. But if you're willing to stay tuned, then welcome to the channel. All right, let's dive into it. And here we've developed a site plan with a pond right here. In the last video, we established the control water level of the pond, but now we're going to walk through the stage storage calculations of this pond and the curve number calculations. Now, the first step of all this is we need to gather the basin area and then do all of the impervious area calcs. We know that this pond's basin is going to collect all of this cul-de-sac because it's the only pond over here. We need to be able to capture all of this stormwater and treat it and attenuate it in this pond. However, from this plan, I can't really tell where the high point break is of the road and of the lot. So we're gonna have to go to some of our sheets to figure out at what station this high point exists. And I will say, when you're doing this early on, even before you create construction plans, a lot of times you're already conceptually laying out some of your low points and high points, so you don't have to have this full-blown construction plan set yet. In fact, you need to do all of your stormwater modeling before you even determine all of the grading of your site, because the stormwater management design elevations affect your road and your lot grades. All right, I need to find this high point, and it looks like we have a high point here kind of by where in between lots 90 and 89. So this is a high point, meaning this is almost like a ridge. So any sort of water that falls within this right of way and within these lots right here go into these inlets and then into our pond system. So typically with residential development, you want to be able to capture all of the lot drainage because you have impervious area within the lots. So when I'm kind of starting with this basin, I'm going to start where our property is right here. It's also a little bit past our right-of-way line. I know that we're going to have to capture, any sort of water that comes here and grades toward the road. So I'm just going to start there. And again, we have to capture all of this lot. And one thing that you could do is you can go all the way to this wetland buffer area, because technically we're grading a little swale here. So all those grades might end up lower than some of these ones. Let's see. It actually doesn't really look like it. So we can start by just picking up this swale. We're going to go behind all of the lots here. And I know what you're thinking. You could probably do all of this in CAD. That is very true. But also you can do it well in with Bluebeam. So again, I'm going around where I know that we're going to capture water. And then technically we're going to have a high point in all of these different lots. If we check the conceptual grading plan, we have higher elevations of 47 to 46. So technically this is a high point right here. I wouldn't want to go past those lots right there. And I know I'm not being perfect right here, but once you hop into AutoCAD, you can kind of perfect all of these if you really want to and make all of the areas perfect, right? So now I have this area, and in Bluebeam, I'm going to change this property a little bit. I'm going to do a fill color, maybe not like that. Maybe I'll highlight it, do some fill opacity down, increase those line widths, and I like to do blue. All right, so our basin is 6.49 acres. We're gonna have to track some of this stuff here in order to do our curve number calculations and then set up our hydraulic model. So this is for pond D. So we're gonna call this basin D, and then this is going to be pond D. And then we have to enter in the total acreage. Well, we know that we got 6.49. And then now what's left is to find any of the building acreage, the pavement acreage, and then the pond's normal water. The building and pavement might take us a little bit more time. I'm going to set those for 0 for now. Let's get the pond normal water level. Again, the pond normal water level is where we expect the water level to be. It's the design control water level based on all the work that we did in the previous video of setting this water line. So if you're confused about what a normal water level is or a control water level, go watch that last video. But we're going to need to take an area of that water line. So let's gather that area. All right, so for the normal water level area, we got 0.4 acres. So let's go ahead and enter that guy in. And then now in order to get our pervious, we have to get the building and pavement, because what we're doing here is we're getting the total acreage, And then we're just going to subtract all of the impervious area to get our pervious. That way we don't have to do redundant calculations to get the pervious. It can just be an easy subtraction problem. Now, in my eyes, the easiest way to get a building acreage is to just multiply all of these lots by the max footprint of the building versus taking a whole bunch of areas. So I'm going to do that. So let's assume for now that this entire pad right here is going to be the building. So we can take one area and let's see how large that will be. So it's about 0.075 acres. So how many lots do we have? We got 1, 2, 3, 4, 5, 10, 20, 21. So we need to do 21 times, let's just call it 0.08. I really love rounding. You do not have to get to the thousands. I hate when engineers get way too deep with that. All right, so 21 times 0.08 is 1.68 acres. 1.68 acres of building. Now the last thing that we need is pavement. And again, I know some of you want to get so nitty gritty in your calculations and you can get this from CAD and you can get a perfect area. You can do that. But sometimes when you're developing these conceptual models really early on, time is of the essence and your site plan is constantly changing. So one easy way to get all of the pavement of this right-of-way is just to get the linear feet of the road and then multiply it by the width of the roadway and all of the sidewalk that you have. Most of the time, it ends up being within 99% of your actual area. All right, so let's get the polyline length. I'm gonna go from here. If you're thinking ahead, we probably could have just gathered the stationing. Now I'm gonna go about right here and then start cutting this as much as I can through this center line as possible. And like I said, I would bet you $100 I would be within 99 percentile if you were to take the exact area. Obviously, this is going to be perfect, but it's going to be good enough for what we are doing in this exercise. So this is around 1,037. I love rounding, so 1,038 linear feet. Now we just need to know this roadway width. And remember, guys, curb is impervious area. So instead of just taking this roadway width between here, I need to add that curb width. So whatever the width is from here to that point, which I know it's 24 feet. In this case, we had 2 feet of curb on both sides. So we're gonna multiply that 1,038 by 24. That'll give us the total roadway. And then we'll do sidewalk next because I just noticed that we don't have sidewalk on both sides. We only have it on one side and then it becomes on both sides. So there's a workaround for this. So 24 times 1,038 is 24,912. We have to divide it by 43560 to get acres. So 0.57 acres. So I'm going to do equals 0.57 acres. We're going to have to add the sidewalk in. You can create another sidewalk row here if you really wanted to. You don't have to. You can just provide a note that says pavement also includes sidewalk. So I'm getting the linear feet around this cul-de-sac, which it's 603. So it's 603 around this cul-de-sac. So 603 times 5 divided by 43560. And then I can subtract my 1038 because that's the total linear feet of all this. I can subtract 1038 feet minus 603, multiply it by 5 to get my sidewalk. So 435 times 5 divided by 43560. So 0.05, let's call it. So that's how much sidewalk I have. So just to do a recap, we got the total acreage, we got our building, we got our pavement, we got our pond. Now what is left? Well, if you can see down here, we have some runoff coefficients and some curve number calculations. Now these are going to be up to you guys. It depends on your jurisdiction, your land cover. You're going to have to verify each and every value that's within here. Now, what I will say, just to start off with runoff coefficients, you typically need this runoff coefficient for any sort of storm CAD or local inlet design that you're doing. You also typically need it for treatment calcs, and we can get to those in a different video. And then you need the curve number calculations for your hydraulic models. So whether you're using ICPR, Stormwise, SWIM, hec-ras, any of those types of models will need a curve number if you're using the SCS method. Now, the higher the C value, the more impervious or the more impermeable, meaning water is not going to soak into that surface. So for a pond, there's no soaking of the surface. It's going right into the pond. It is having a high C value, and same for curve number. It is at 100 because it is not permeating into the ground. It's going right into the pond. Now with pervious, the C values can vary anywhere between 0.2 to 0.5. It really depends on your land cover. Same for the pervious CN. This is heavily dependent on your land cover, and I highly recommend you guys learn as much as you can about the TR55 manual. I'll put a link in the description. This goes over everything you need to know about stormwater. It even tells you all your curve numbers that you need to use. See right here? Curve numbers for rangelands, curve numbers for agricultural lands, and so on. So we're basically halfway through. We've developed our curve number that we're going to have to input into our hydraulic model, but now we need the pond stage storage. That is one of the very last things that we need. So what does stage storage even mean? So with all these descriptions right here, these are all of the elevation types. It's going from top to bottom to the lowest elevation to the highest elevation. So we're going from a bottom elevation to a slope break elevation, which is typically a point in the cross section of the pond where the slope changes. Then we have the normal water level elevation. Then we have the top of bank. Well, we can begin to pull some of this information already because we have an idea of what we set the normal water level to, and we have an idea of how we should set our top of bank, and I'll talk about this. So let's go back to our pond. In the last video, we set this normal water at 41.9. So I'm going to go ahead and enter that guy there. Now, depending on your cross section of the pond, you can set the top of bank to whatever you want. However, it's your job as the designer to not over design your pond. Also, you can't exceed maximum slopes. Typically for these types of pond designs, you can't exceed 4:1 or 25%. So if you had 20 feet of horizontal room, if I grade 4:1 max, I can only go 5 feet high. So the highest that I can set this top of bank to is 46.9 solely based on slopes itself. So when I'm starting these models out, I typically like to set it anywhere between 4 to 5 feet high, run my models, and then start dropping the top of banks to meet my minimum freeboard and to make grading work and all that, but that's not in this video. All right, I'm going to erase some of these other values. So we do know, in fact, the normal water level area. I'm going to equal that to this one because we already found it. But now we need the top of bank acreage. So let's go back to our plan set and let's get this acreage right here. The top of bank is where we're trying to keep water within the stormwater management system. It is essentially the highest design point of the pond where we're trying to contain the design high water levels. So that ends up being 0.588, and I'm going to call it 0.6. Now, I actually kind of just want to stop here. I'm not going to walk through the bottom elevations and the slope break elevations right now because right now they're not needed. These are typically needed for your treatment calculations, but we're not doing those today. I wanted to be able to walk through how to gather basin information, curve numbers, and stage storage calcs for a hydraulic model. You don't need a slope break elevation or bottom elevation for a hydraulic model because our control water level is the very starting point of our model. When we input this into a model, that is going to be the initial stage at where we start the model. And once we snap the fingers and turn on the model, the staging is going to increase from there. So any elevations below that do not really matter. So I'm going to save these things for another video. Now, the reason why I have this column right here is because I really love to understand the volume between the normal water to the top of bank. The reason being is because you can do a static calculation of how much volume you think is going to be generated from your basin into this pond. Now, it's not going to be perfect and it's not going to be like how a hydraulic model spits out because a hydraulic model is factoring in things like percolation and then the weir that you input. But I want to show you just to do a check of if your pond is even big enough at the very start. So we have 2.5 acre feet between the normal water and top of bank, and we have a total acreage of 6.49 acres. Now, a design storm event of a 25-year, 24-hour in this area generates about 8 inches of rainfall. So 8 inches of rainfall. Well, 8 inches is also 0.67. 0.67 feet times your whole basin area of the 6.49. That's about 4.35 acre feet of volume of water that's going to go into that pond, 4.35. And we only have 2.5 right here. Now, this isn't the end of the world. If you were to do a static calculation here and just do how much volume do I have versus how much of that bowl is going to get filled up, well, it's going to spill over the top of bank. But luckily, we have weirs in control boxes that once they reach certain levels, they go into the box and then into the outfall. So off the bat, this isn't the end of the world, but I know that we're going to have to put a weir inside the pond to control the staging of the system. Now let me show you that really quick. So right here, this is a control box right there. It is a control box that's controlling the rate of this pond. So when we enter this in our hydraulic model, we're going to be entering in a few very important details. We're going to enter in the normal water level, our preliminary top of bank. We're going to enter in the basin area, and then the CN, and then finally the time of concentration, which is last on our list. Then you can actually set up this pond in a model and get it to run. All right, last but not least, we have time of concentration. So what is time of concentration? Time of concentration is the time it takes for a little rain droplet from the furthest point of the basin to travel into your water body. Now, at the very start of that water droplet, water acts as sheet flow, but it only acts as sheet flow for the first 300 feet. So that's why I have this little guy right here, less than 300 feet. And it is dependent on a Manning's roughness coefficient. It's dependent on your 2-year 24-hour rainfall in inches, a length, and a slope. And then all of this determines the sheet flow time. So if you go to your little table over here, you can determine what your roughness coefficient is. But first of all, how do I even know? Like, where do I even get this information? How do I know where to start the point? That's a great question. Where will the most furthest little rain droplet fall and then go into our system? It looks like a couple of places. I'd first start maybe right here at this high point. Looks like a water droplet wants to fall here, fall there, and go there. Let me fatten that up just so you guys can see it. So that's a water droplet there. And guys, you don't have to be absolutely perfect, but it has to make sense. So here's a high point here. That's a low point. So high point here, it goes into the road, travels along the gutter line, and then finally into this curb inlet system. And a lot of times I don't factor in the travel time in the pipes because this system is already submerged with water. This normal water level is already within the storm system. And sometimes you'll have to create a few patterns here and pick, what the longest one is. But to me, just from my eyes, it looks like that's the longest. So we're going to go with that one. And like I said, the first 300 feet is sheet flow. So if this starts getting longer than 300 feet, it becomes channel flow, and then we need to go on to the second part of the calculation. Let's check this spreadsheet out again just to make sure we're on the same page. So our Manning's in, it's first starting out in a grassy lot. So I think I'm just going to go with this grass here, short grass prairie. I mean, it's even going to be more smooth than that, honestly. As long as you can back up your calculation, that's the most important thing. You're going to have to figure out your 2-year 24-hour rainfall. I can make a whole nother video on that. You can go to NOAA. Now, what was that length and then the slope? So this length right here from this high point all the way down to where the curb line is, it's about 252, let's call it. So 252. And then at what slope? So 252, elevation 47.22, all the way to some grade. Okay, let's call it the 45. Let's call it elevation 45 right there. The 200s don't really matter. So 47.22, this is just a slope equation. Minus 45 is 2.22 feet of drop divided by 251. So 0.0088. I'm going to round to 0.01. That's foot over foot. That's not, a slope percentage. That's foot over foot. So that's going to be barely any time. And if you think about it, that's barely any time. Oh, the Manning's in. That's why. See, always double check your work. I should be at 0.1. Okay, that makes way more sense. Also, look at those relationships. The higher your Manning's in, the slower the time is, right? Because it's roughness. The slower water moves across that surface. But then we have the next part. So we're done with the sheet flow. After that sheet flow, it turns into concentrated flow, and it can either be unpaved or paved. Well, in this case, we have paved because it hits a roadway right there at that curb. So let's get that linear feet. It's roughly 25 feet. All these roads in these neighborhoods are graded at a minimum 0.35% longitudinal. So this slope foot per foot is 0.0035. So that barely did anything. So our total time of concentration is 16.9, also known as 17 minutes. And there we have it, guys. We have walked through our basin delineation, the land use, which is your acreage breakdown of all your impervious area, your runoff coefficients, curve numbers, stage storage, and then time of concentration. You have to do these and stay organized with each and every pond that you design, and then you'll plug those into your hydraulic model. And obviously you'll have to set up some boundary conditions, but that'll be in a later video. And honestly, that's it. I hope that this video helped you guys. If you have any questions, please comment below and I will be glad to answer each and every question. If you haven't checked out my land development series, I would go to that playlist and start wrapping your head around land development. I touch on a lot of different topics, like how to read plans, how to do a pre-development analysis of topography, and a whole bunch of other stuff. That's all I have for today. I hope you guys learned something new, and I will see you in the next video. Peace out.